Hi everyone, my name is Fiona and today I'll be talking about acoustic cryptanalysis, which is a type of side channel attack that exploits sounds generated during cryptographic computation. We'll be focusing on this RSA key extraction attack created by Genkin, Shamir, and Tromer in 2013. They discovered that it was possible to extract full 4096-bit RSA decryption keys from laptops by listening to the sounds generated during ciphertext decryption. This attack can be completed within an hour and it targets GNU-PG, which is a common open source RSA implementation. At the heart of this attack is the fact that computers emit a high-pitched noise from the voltage regulation circuits during computation. This sound is related to the CPU's change in power consumption depending on the operations they're executing. Attackers can use a computer and microphone up to 4 meters away or a phone placed 30 centimeters away to extract a target's RSA keys. Once the attacker has these keys, they can read any encrypted messages the victim receives. We can compare this side channel attack to earlier related attacks. Keystroke timing patterns have been shown to reveal the identity of users and the information that was typed, but this technique requires that the data be typed out. Acoustic emanations from dot matrix printers can leak information that was printed. In fact, this attack can recover 72% of English words, but this type of technique does not work on randomly generated passwords. Brumley and Bonnet performed an RSA timing attack against OpenSSL that was very similar to this GNU-PG attack. However, compared to acoustic attacks, timing attacks are relatively easier to defend against by adding delay cycles. Historically, acoustic leakage from electromechanical devices like keyboards and printers have been well studied, but exploiting acoustic leakage from modern electronic components like voltage regulators is more novel. Here is a quick review of RSA since we covered this recently in class. This is a version with a 4096-bit key. We first generate two random primes, P and Q, each of which is 2048 bits long. Then we calculate n as P times Q, and we generate public and secret exponents E and D. Our public key is E and N, and our secret key is D, P, and Q. For this attack, we'll be targeting decryption, which is the operation C to the power of D mod N for a given ciphertext C. Because this is such a tedious calculation, GNU-PG splits decryption up into two operations. The algorithm computes two constants dp and dq, then performs a mod p and mod q computation separately, and later derives the plaintext m through some manipulation. The acoustic attack exploits this mod q step to steal q, because this operation has a very distinct acoustic signature. Let's say the attacker wants to use a phone to extract the private key Q from a target laptop. The laptop must be running some program that automatically decrypts encrypted messages. These researchers used Enigmail, which is a plugin for the Thunderbird email client that provides message encryption. At a high level, the attacker sends one email at a time, containing a special ciphertext to the target. Enigmail running on the target automatically decrypts each incoming message by default. Then the attacker listens to the sound that the target emits and gains some information about Q. This leads us to the question, how do we actually choose our ciphertext in the first place? Let's say that we want to reveal the private key Q one bit Qi at a time, from most significant to least. We know that the most significant bit of Q will always be 1. Then for each bit Qi and Q, assuming that we know the previous I-1 most significant bits of Q, we choose ciphertext Gi to be the 2048-bit long number according to the following rules. The topmost I-1 bits are the same as those recovered from Q so far. The ith bit is 0, and the remaining bits are 1. For example, if we're trying to uncover the second most significant bit Q2, then we send the ciphertext G2 such that the first bit is 1 to match the part of Q we know, the second bit is 0, and then the remaining bits are 1. This is the ciphertext we send to the target to reveal Q2. We can take a look at the simplified pseudocode of the GNU-PG decryption implementation to see why this ciphertext choice works. This method performs a modular exponentiation c to the power dq mod q, which the target uses to partially decrypt C. Using the same example from before, we'd like to see why sending the specific ciphertext G2 reveals the second bit of Q. G2 is initially passed into the algorithm as C. Because of this first step that computes C mod Q, C may take on two different forms depending on the value of the mystery private bit Q2. If Q2 is 0, then this C mod Q operation causes C to change and become smaller and more random looking. However, if Q2 is 1, C remains the same after this operation. This is important because each multiplication of C in the following loop causes the computer to emit different sounds depending on if the Q bit is 0 or 1. This pattern is true for any ith bit of Q. Here we have frequency spectrograms where the horizontal axis is frequency and the vertical axis is time. The graphs show the emissions during decryption when Qi has the value of 0 versus 1. If these frequencies were shifted into the audible range, when Qi is 0, the emission may sound like this. And when Qi is 1, the emission may sound something like this. During decryption, mod P's acoustic signature, shown in orange, does not really change depending on Qi, but mod Q's signature, shown in pink, is different enough for us to determine the value of Qi. We can summarize all of this into the attack that researchers use to extract Q. To uncover each bit Qi and Q, email the ciphertext GI to the target laptop. Record the audio while the target automatically decrypts the message. Then decide if the current Qi is 1 or 0. After we've uncovered all the bits of Q, we can factor out P from N and calculate D to form the complete private key. Now let's do a demo of this where we are the attacker. In this example, we're using a phone to attack a victim's laptop. The victim is using the Thunderbird email client, and let's say we somehow discover the victim's email address. We begin the attack by extracting Q2. So we send an encrypted email containing G2, where the first bit is the same as Q1, the second bit is 0, and the rest are 1s. The target automatically decrypts the email, and it emits an acoustic signature during its computation of mod Q. We use our phone's built-in microphone to listen to the sound. Let's say that the target emits a lower frequency noise, so we determine that Q2 must be 0. Next, we use this information to attack the next bit, Q3, using the new ciphertext G3. Now we set the first two bits of G3 according to our discovered Q bits so far, then the third bit is 0 and the rest are 1s. Again, we listen to the sound. If it's a higher frequency noise, we determine that Q3 must be a 1. Performing the same thing for Q4, if the target now emits a higher frequency, Q4 must be 1. We can continue to do this for the remaining bits of Q. All of this can be packaged into a program that automatically constructs ciphertext, sends emails, and classifies these bits. Eventually, we can do this 2047 times, which takes about an hour. Then we have the complete 2048-bit value of Q. Finally, we can calculate N and D, and we'll have the full private key of the victim. Now that we know how the attack works, let's take a look at possible defenses. One possibility is acoustic shielding, but this poses a challenge because blocking sound likely blocks air circulation too. Another possible mitigation is adding extra loads on the CPU to disguise the acoustic leakage. However, as you can see in the graph, this really only shifts the range of the leakage, but doesn't mask it. The defense that is effective is ciphertext randomization. During key generation, this would generate another random value R. Before encryption, we would multiply the ciphertext by R to the power of E, and after decryption, factor out the random value. This poses a new challenge because R changes the value sent to the modular exponentiation algorithm, which then breaks the attack. To summarize, the main takeaway is that within an hour, we can extract the complete RSA decryption keys from laptops by listening to the sounds emitted during decryption. This is a dangerous attack because it has simple and discrete setup that works against many different laptops across vendors and models. The entire attack could be put into a mobile app that the attacker installs. They could just leave their phone near someone's laptop, like during a meeting or in a coffee shop, and let the app perform the hack. The attacker could also eavesdrop with a compromised phone or a cheap book. The recent new PG versions have patches against this attack, so we can no longer extract the full keys, but we can still distinguish one key from another. This attack demonstrates that even though RSA may be theoretically and mathematically secure, Information about the private keys is still revealed through the implementation of the cipher. Thank you so much for watching.